Have you ever wondered about this? There's this invisible energy battle happening all around us, like every single second. It's the secret behind why a campfire feels so warm, but an ice cube makes your hand feel freezing. And trust me, once you get it, you are going to see the world in a completely new way. Let's dive in.
So let's just break it down to this simple question. A campfire gives off heat, right? It warms you up. An ice cube does the total opposite. It makes your hand feel cold. They're both just things. So what is going on here? What's the secret?
Okay, to solve this mystery, we need to crack a kind of secret code. And believe it or not, the entire code is really just built on two words. If you can master these two words, you'll have the key to understanding how energy works pretty much everywhere.
And here they are, exothermic and endothermic. Just think of them as total opposites. Exothermic reactions release energy, and they heat things up. Endothermic reactions, on the other hand, absorb energy, and they cool things down. One is a giver, the other is a taker. Let's talk about the giver first.
First up, exothermic. The easiest way to remember this is that exo sounds like exit. See? The energy is exiting the system. A campfire is the absolute perfect example of this. It's not creating energy out of nowhere, it's just releasing all that stored up energy from the wood as heat and light. And that warmth you feel, that's the energy exiting.
So, the opposite is endothermic. And you probably guessed it. Endo sounds like enter. The energy is entering the reaction. It has to literally pull in energy from everything around it. A chemical cold pack is a great example. You know, when you snap it, the chemicals inside start sucking in heat from the air and from your skin, which is why it feels freezing cold.
Okay, so one releases energy, one absorbs it. Got it. But why? To really get this, we need to visualize it. And honestly, the best way to do that is to picture an energy roller coaster. So strap in.
So check this out. Every single chemical reaction is kind of like pushing a boulder up a hill. That first big push you need just to get it to the top. In chemistry, that's called activation energy. But once it's at the very peak, it can just roll down the other side all on its own, releasing a ton of energy as it goes. Every reaction has this uphill push and this downhill roll.
And this is an exothermic reaction. See how the starting chemicals, the reactants, are way up high on the energy hill. It just takes a little nudge to get them over that peak, and then, whoosh, they race downhill to a much lower energy state. That huge drop, that is all the heat and light that's pouring out of the reaction.
Endothermic reactions, they're the complete opposite. It's an uphill battle the whole way. The reactants start at the bottom, low energy, and to get to the finish line, the high energy products, the reaction has to constantly suck in energy from its surroundings just to keep climbing. That's exactly why it feels cold. It's literally stealing your body heat to power its climb up the hill.
Now, this isn't just stuff that happens in a science lab. This energy roller coaster is happening all the time with the most common thing on Earth, water. Let's see how this all applies to plain old ice, water, and steam.
Just think of the states of matter as an energy ladder. Down at the bottom, you've got solid ice, super low energy. All the molecules are locked in tight. In the middle, you have liquid water. It's got more energy. The molecules can flow around. And way up at the top is steam, the highest energy. Molecules are just flying all over the place. Now to climb that ladder, from ice to water to steam, you have to add heat. That's endothermic. And to go down the ladder, energy has to be released, and that's exothermic. So what does this actually look like in the real world? Well, melting and boiling are endothermic. To melt a snowman, heat has to go in. Makes sense, right? But condensing and freezing are exothermic. You know how a cold glass gets all wet on the outside on a hot day? That's water vapor in the air turning into liquid on the glass. To do that, it has to release heat. That's heat coming out.
But all of this leads us to the biggest question of all. Why? Why does melting need energy? And why does freezing release it? The answer is the single most important rule in all of this. I like to call it the golden rule of bonds. And here it is. This is it. This is the key to everything. You ready? Breaking chemical bonds always, and I mean always, costs energy. And making new chemical bonds always releases energy. Every single reaction we've talked about is just a game of breaking some old bonds and making some new ones. So let's apply the rule.
To melt ice, you have to break the bonds that are holding all those water molecules together in that crystal shape. And what's the rule? Breaking bonds costs energy, so it has to absorb heat from its surroundings. That's an endothermic process. Now, to freeze water, you're doing the opposite. You're making new bonds to form that ice crystal. Making bonds releases energy, so heat flows out. That's an exothermic process. See?
So now that we have the golden rule, we can finally go all the way back to the beginning and solve our original mystery.
So, the campfire. Yeah, burning wood breaks some bonds, but the key is that it makes a bunch of new, super strong bonds in carbon dioxide and water. The energy released from making those new bonds is way, way more than the energy it took to break the old ones. And that extra energy is the massive amount of heat you feel. It's powerfully exothermic. And the melting ice cube? It's simply taking heat from your hand to do one job: break the bonds holding the ice together. It's a textbook endothermic process.
So there you have it. It's not magic, it's just chemistry. The whole secret of hot and cold is just a story about making and breaking bonds. Now that you know the rules, what else can you explain? You know, why does cooking an egg require heat? Why do you shiver when you get out of a pool? The answer's always hiding in the energy exchange.